Hi, my name's Adam Tempshin, and I'm from Washington, D.C. I'm very studious and I love math. I can't wait for junior year to start, and I don't know what's in store, but I know it's all going to be okay, because I'm 16 and in calculus. Well, first I would like to show you my learning method as opposed to Miss Bento's learning method. It is smile, 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 and learn. Very revolutionary and very nice and happy. Alright, so continuity. What is continuity? Basically it is the assurance that every single point on a graph is following the pattern. Basically, the simple definition is a continuous graph is any one where you can draw it entirely without having to lift up your pencil or pen. And so that would be a continuous function. And so there are three ways to prove that it is, three steps to proving a function is continuous. The first step is, number one, is all points f of c exist. And so basically that means every single point on the function exists. So there are no holes, there are no asymptotes, and so every single x value gives you a y value. And then the second condition is the limits exist from both sides. So limits of f of x as x approaches c exist. And that's both limits, both the upper and the lower. So if they're not the same, or one of them does not exist, then it is not a continuous function. And the third and final condition of it being continuous is that is the limit of f of x as x approaches c, is it equal to f of c? And so that basically means that the limits that you found before equal the actual point, and it is not a point discontinuity, which I will show you later. All right. So now that we know the three conditions of continuity, we can look at some discontinuous functions, some known discontinuous functions. Okay, so the first function we'll be looking at is jump discontinuity, and so it's basically a graph where all the points exist, but there is a step or a jump in the graph, and then it continues, like in this graph. So call this point 2. So it goes up until x equals 2, and then it skips up to another number, and there you can see there's a hole there, and this is the number down. So this is the y value of this number of 2. And so if you were looking at the rules, the reason it doesn't pass the rules is because all points do exist. There is a point for 2 right here, and there is a point for everything greater than 2 and everything less than 2. So it does pass the first condition. But the second condition, limits exist from both sides and they're the same, is not true, because the limit from this side is, well, this number, let's call it 3, and the limit from this side, coming from this side, is not 3. It's more probably something like 4. And so this does not pass the test. We don't even need to move on to the third condition, because it already doesn't pass the second condition.
Go.
Okay, so the next continuity we'll be talking about is point discontinuity, and is when there's a hole in the function and then there's a point above it as that point. So let's take this function for example. There is a hole at x equals 2, and then there is a point above instead of this hole. And so we put it to the first test, if all points on f of x exist, and in fact they do, because as you can see, everything less than 2 and everything greater than 2 exists on this line, and then 2 also exists above the equation. So it passes the first rule. The second rule is that are there limits approaching from both sides? And the answer is yes, because as x approaches 2, the limit of f of x is 3, the upper limit, and then also the lower limit also equals 3. And so then we take it to the third rule, which is, does the limit as x approaches 2 match the limit of the actual point? And the answer is no, because the limit as f of x as x approaches 2 is 3, while the actual point, as you can see, is at 4. So 4 does not equal 3, and so it does not exist. Alright, and that brings us to our next graph, which is a vertical asymptote, or also known as essential discontinuity. And it is when a equation is going along and hits a vertical asymptote, hits a vertical asymptote like that. And so these lines are approaching this middle line right here infinitely, and but they're never touching it. So immediately we can say it is not continuous, because not every point exists. Because this is at x equals 2, there is no y value because it is an asymptote, and so every point around it exists, except every point lower than it exists and every point greater than it exists, but it does not exist because it is an asymptote. So we can just get rid of that one immediately. Alright, and then the last type of discontinuity is like the point discontinuity, except there is no point above the equation. So it is it's called hole, and it's just a hole. And as with the vertical or essential discontinuity, not every single point on this line exists, especially at x equals 2. And it does not exist, as you can see. So it does not pass that first test. And so that's all the graphs you're going to run into with according to discontinuity. Okay, so the next thing we'll be talking about is the intermediate value theorem and the extreme value theorem. Both of them are theorems that are true when the function when you know that the function is continuous. So the actual definition is very long and verbose. It's if f of x is continuous for all x in the closed interval a through b, and y is a number between f of a and f of b, then there is a number x equals c in a comma b for which f of c equals y. So that's a very complex way of saying that that if it is a continuous function, from the points A to point B, then there's a point C, which is right here. Then there is a corresponding y value for that C that is also in between f of A, and f of B. So basically the x values, for it. So if C is in between the x values, the y is also in between the y values. So you can't have a point that's, if a function is continuous, you can't have a point that's all the way up here, because C is not, because the f of C is not in between, and so therefore the function is not continuous. So that So the intermediate value theorem is not true. Alright, and then next we move on to the extreme value theorem, which is similar to the intermediate value theorem. It's also on a works with a closed interval. So let's just draw, let's say, a parabola right here, and this is A, and this is B, A, B, and it is a closed continuous interval, so there's no breaks, there's no jumps, there's no steps. It is just a continuous function that then it has both a minimum and a maximum value. So as you can see here, the minimum value is A and B down here, and the maximum value is up at the top of the equation up there. And let's say, and it works the same way for an equation, a non-parabolic equation like this. If B was up there, you know, it would still have a minimum and maximum because A is the minimum and B is the maximum up here. Okay, so this is a common multiple choice question that will show up on the calculus exam that pertains to continuity. It is this sort of piecewise function where you're going to have to fill in k to to make something true. So in this particular equation it says for what value or values of k is the function continuous at x equals 3. And as you can see here, it has the equations for everything less than, -3, and the equation, oh, that's supposed to be negative right there, and the equation for everything that's greater than -3. And you have to basically make this point make this point so it connects these two lines, these two functions. And so to do this, we just we use the three conditions that we talked about earlier to make this k to make it continuous. So the first condition, remember, is all points exist. And so it's simple to do that. You just do f of -3 equals k squared minus 5k, saying that when x equals -3, there is some y value according to this equation. So that justifies all points exist. So number 2, there is a limit. There's a limit as x approaches c of f of x, and that is true. There are two limits coming from both sides, and they both actually, if you look back over here, they meet at the same point, because if you evaluate this one for -3, you will get 18 minus 12, which is 6. And if you evaluate this one for -3, well, there's no place to put that -3, so it'll just be 6. So they're both 6, so the limit of the function equals 6. So the limit of the function equals 6. And so to just, and then we move on to our third condition, which is the limit of x as it approaches c of f of x equals f of c. And so this is our equation for f of c up here. So all we have to do is set 6 to equal k squared minus 5k, and then we simply solve it by making it into a quadratic function and finding the zeros. So 5k minus 6, and then the zeros are x minus 6 and x plus 1. And so, k. And so the two values for k you get are positive 6 and -1, which is our option A over here.